Broken laptops, outdated televisions, and shattered smartphones may seem like worthless waste at first glance. But in reality, they contain an enormous hidden value that the world is only beginning to fully understand. Every year, electronic waste generates over $80 billion in recoverable materials, enough to reshape entire industries. In 2024 alone, humanity produced more than 62 million tons of e-waste, yet only about 20% of it was properly recycled. The rest is not only wasted but also silently contaminates the environment with toxic elements like lead, mercury, and cadmium. However, inside massive industrial facilities, a different story unfolds, one where waste is not discarded, but reborn into one of the most essential materials of modern civilization: steel. The recycling journey begins in the most familiar places: homes, offices, schools, and electronic trade-in programs. These seemingly obsolete items are collected and transported to large-scale processing facilities. Upon arrival, each batch is carefully weighed, labeled, and entered into a tracking system before undergoing initial sorting. Devices are categorized into groups such as IT equipment, display units, and large household appliances to optimize downstream processing. Although this is just the first step, it is critically important, as accurate sorting directly impacts the efficiency and effectiveness of the entire recycling operation. At this stage, everything still appears chaotic, as thousands of devices of different shapes, sizes, and conditions converge in one place. Scratched laptops, cracked screens, and outdated electronics pile together, resembling nothing more than meaningless scrap. But to the processing system, this is not simply waste, it is raw material waiting to be unlocked. Each item contains hidden metals, stored energy, and economic value that remain trapped within its aging shell. The mission of the facility is not just to process these items, but to systematically break them down, analyze them, and release their full potential, preparing them for the transformation ahead. Despite rapid technological advancement, human labor remains irreplaceable during the dismantling phase. Each electronic device has a unique structure, requiring adaptability and precision that machines cannot yet fully replicate. Workers carefully remove plastic casings, separate metal frames, extract circuit boards, and detach wiring systems. During this process, functional components such as RAM modules, hard drives, and motors are recovered for refurbishment or resale. Notably, metals like copper extracted at this stage can reach purity levels as high as 99.99%, making them extremely valuable for further industrial use. This is the stage where human work relies not only on skill, but also on experience and intuition. A single mistake, one overlooked component, can put the entire downstream process at risk. That is why every action is performed with intense focus, as if each device is being carefully decoded. And once the outer layers are removed, what remains is not just material, but the true core of the device where both value and risk coexist. Because within it, hazardous components still exist, and they must be carefully removed before machines can safely take over. Before mechanical processing begins, all hazardous components must be completely removed to ensure safety. Lithium-ion batteries pose one of the greatest risks, as they can explode at temperatures reaching 1,800 degrees Fahrenheit if crushed. Additionally, refrigerants like Freon from refrigerators and air conditioners are extracted using specialized equipment to prevent environmental damage. Older CRT displays are also carefully dismantled to avoid releasing toxic lead dust and mercury vapor. This step is essential for minimizing risk and ensuring that all subsequent processes can proceed safely. This is the thin line between a controlled process and an industrial disaster. A single missed battery or a trace of hazardous material left behind could compromise the entire system that follows. That is why every detail at this stage is tightly controlled, from handling procedures to protective equipment. Once the final hazardous components are removed, the remaining materials are finally considered safe for mechanical processing. And from this point on, everything changes, no longer defined by human precision, but by the raw power of massive machines ready to break everything down into raw material. Once hazardous materials are removed, the remaining components are fed into a two-stage shredding system. Here, they are reduced into uniformly sized fragments under tightly controlled conditions, allowing processing capacities of several tons per hour. From this mixture, advanced separation technologies come into play. Industrial magnets extract iron and steel, while other systems continue sorting aluminum, plastics, and various metals. This is one of the most critical stages in the entire process, as steel represents the largest portion of e-waste and serves as the primary input for the next phase. At this point, nothing resembles its original form anymore. What were once complex devices, phones, computers, electronics, have been reduced to raw, clearly separated materials. Yet this act of destruction is exactly what makes transformation possible. Because once everything is broken down to its fundamental state, iron is iron, steel is steel, metal is metal, true regeneration can begin. This is the moment when waste stops being waste and becomes raw input for an entirely new industrial cycle. And from here, these fragments of metal move into the most intense phase yet, where extreme heat will reshape them into something entirely new. The recovered steel is then fed into an electric arc furnace, where temperatures can exceed 2,700 degrees Fahrenheit, enough to fully melt the metal. In its molten state, impurities rise to the surface and are removed, leaving behind purified material. Engineers then add elements such as manganese, nickel, or chromium to fine-tune the steel's mechanical and chemical properties, ensuring it meets strict industrial standards. At this point, electronic waste has undergone a complete transformation, no longer scrap, but a high-value engineered material. In the moment metal turns liquid, almost all traces of its past are erased. No more phones, no more computers, only a pure mass of material moving under extreme heat. This is where value is no longer defined by its original form, but by how it is controlled and re-engineered. Every slight adjustment in temperature, every added element, shapes the final outcome. And here, the line between waste and resource disappears as everything is melted down to begin again from zero. After refining, the molten steel is cast into billets and undergoes hot rolling. These solid blocks are reheated and pass through massive rollers, where they are stretched, compressed, and shaped according to specific requirements. The result is a range of products such as steel sheets, coils, and reinforcing bars, used across industries from construction to manufacturing. This is the stage where the material truly takes on a new form, ready to enter its next life cycle. This is the moment where metal is not only reborn, but given a new identity. From a formless state inside the furnace, it now takes on precise, measurable shapes. Every sheet, every bar of steel is no longer random, but the result of a tightly controlled process from beginning to end. And it is here that true value begins to emerge, as material once discarded is now ready to become part of buildings, machines, and the infrastructure of the modern world. But before it leaves the facility, one final test remains. Before reaching the market, finished steel must undergo rigorous testing, including tensile strength evaluation, flexibility checks, and chemical composition analysis. Only materials that meet strict standards are approved. Recycling steel not only reduces waste, but also saves up to 75% of the energy required compared to producing it from raw ore. Today, approximately 40% of the world's steel supply comes from recycled materials. This means that the devices we discard today may become the buildings, bridges, and vehicles of tomorrow. And as the final steel products leave the production line, their journey is far from over in many ways. It is only just beginning. Materials that were once discarded will continue to exist in new forms, becoming part of skyscrapers, bridges that connect distances, or even the electric vehicles of the future. In a world of increasing consumption, this process is not just a solution to waste, but a redefinition of value itself. Because at an industrial scale, nothing truly disappears. Everything is simply waiting to be transformed. Millions of tons of electronic waste, once seen as the end of a life cycle, are now the beginning of something entirely new. Inside blazing furnaces, the past is erased, forms are broken down, and value is redefined from zero. This is not just a story about technology, but about how humans have learned to control matter itself, turning chaos into order and discarded objects into the foundation of an entire world. What once sat in landfills now supports skyscrapers, connects bridges, and moves with the future. And perhaps the most remarkable part is not that steel can be made from waste, but that nothing was ever truly thrown away. We simply didn't know how to transform it yet.